Live. Hello, everyone at home. Welcome to the final open evening of 2021. You're back with Cambridge University Astronomy, and I'm here with Dr. Annelies Mortier, who is a senior Kavli fellow in exoplanets, and she's going to be telling us all about detecting exoplanets, other worlds beyond our solar system. So over to you, Annelies.
Thanks, Matt. So hi, everybody at home. As Matt said, I'm Annelies Mortier, and I will be talking about how we detect exoplanets. And exoplanets, in case you don't know, are planets that are orbiting stars other than our sun. So there's 8 planets in the solar system, and then there's a whole bunch of exoplanets around all the other stars in the universe. By the way, I love this picture. It'll come back in the presentation if you wonder what it's all about. So back in the old days, there were various opinions about the existence of other worlds, and even the wonderment whether we were alone. It's something that every human being at some point in their life has probably wondered. Are we alone in the universe? Is this it? Now, 2 of these wildly different opinions, one was by Epicurus, who said that there are infinite worlds, both like and unlike this world of ours. And then there was also a statement from Aristotle that there cannot be more worlds than one. Now, no offense to Aristotle, but in this case, Epicurus seemed to have been correct all along, because we found in the meantime so many exoplanets. In 1992, almost 30 years ago, there was the very first proof that there are other planets outside of the solar system. Now, this dissection in 1992 was a pulsar planet. So it's basically a planetary body around a pulsar system, which are these very violent stars that very rapidly spin and give away these pulses. So not quite the type of planet we would want to live on, or not even the type of planet where we would actually think of finding life as we know it. But that was the very first proof that the solar system planets are not alone. And then now in 2021, we found almost 5,000 different exoplanets. This is just a small snapshot of all the different kinds of planets that we found. So there's large planets just like Jupiter, there's smaller planets, there's planets in between. One thing that we've learned in the meantime is that there's so much more variety than what we find in the solar system, which is really cool, obviously. Now, this is an artist impression, because taking a picture of an exoplanet is not actually that straightforward. If we were to take a picture of an exoplanet, this is what it will look like. So that little blob thing in the middle here, that is the attempt of taking away the star. And then the nicely labeled bright dots that you see here, B, C, D, and E, are the planets that orbit around that star that was taken out of the picture. As you see, it's nothing more than just the blob that you can see. And because that star is in the way, taking a picture of an exoplanet is really like trying to take a picture of a firefly next to a lighthouse. And you can imagine how terribly hard that is. So in the majority of cases, we don't actually take pictures of our exoplanets. Now, just to show you what I mean, these are parts of the exoplanets that we found for which we know their mass, which is represented on the y-axis, and for which we know their orbital period on the x-axis. So as a reminder, the orbital period of the Earth is 1 year, it's 365 days. So what you see here in different colors is the different detection methods. And the ones that I just show you, like literally, let's take a picture of an exoplanet, are the blue stars here. So you can see, first of all, there's really not that many. And second of all, it's really limited to very massive planets and also very far out planets. Obviously, that makes sense because the farther away you are from the star, the farther away the firefly is from the lighthouse, the easier it is to actually get it in the picture. So the direct imaging technique whilst cool because you can take a direct picture of your exoplanet and then learn quite a lot through that, it is still pretty hard to do for small planets or closer in planets. The other thing that you see is that this picture is mainly green and red. This is mainly the radial velocity and the transit technique, which I'll talk about in a second. And finally, the other thing you see is that there's really dots on this plot roughly everywhere. So as I said, we do find a whole variety of exoplanets out there. But back to these techniques. So let's start with the radial velocity technique. I'm starting with that one because after that pulsar, it's the first technique that actually detected exoplanets on a regular basis. And it's based on the wobble of a star. So if you imagine that you have a planet orbiting a star, what actually really happens is that both of them orbit the center of mass. Now that center of mass is obviously really close to the star because the star is the most massive thing in the system. But if you have a planet around the star, as an effect, there will be a small wobble of that star, and that wobble is something we can measure. So if we measure the velocity of a star and we see it coming towards us and away again, and towards us again and away again, and so on and so on, if we measure that velocity, then we can infer the mass and the periodicity of a planet that is orbiting that star, creating that wobble. So to get that velocity is basically looking at blue shifted and red shifted light. What do I mean with that? Now, if you have a star, the light coming from that star, from the inside of a star, if you split that up across all the visible, then you basically have a rainbow. So you see everything from the purple to the red. You have a nice little rainbow. Now when that light passes through the atmosphere of a star, so every star has an atmosphere, the outer layer of a star, essentially. If it passes through that, then there's all different types of atoms and molecules that grabbing pieces of the light at specific wavelengths in the spectrum. So your rainbow will essentially, by the time it reaches us, our rainbow will have all these absorption lines, all these dark bands that you see. So that's one way to study stars. Now, if stars are moving back and forth, basically what happens with these lines is that they shift more to the red if the star moves away from us, and more to the blue if the star comes towards us. So because we sort of know which lines we're supposed to look at and where they are supposed to be if the star would be standing still, then we can take such a spectrum, look at the lines, see how much it was shifted, and get that velocity at that particular point in time. And then we do that again and again and again and again and again, up until we hopefully have this nice little curve where you can see that the velocity wobbles over time, and then we can model that to get out the planetary properties. Now, a couple things to note. The redshift and blue shifted lines here is highly exaggerated. If you would plot that, what really happens with the wobble of a star because of a planet, you wouldn't actually see anything happening by eye. So those shifts are seriously small. These are just exaggerating for explanatory purposes. Now, just to give you an idea of the kind of velocities I'm talking about, our own Jupiter around our sun, if an alien were to try and look for that, they would see a velocity change in our sun of about 12.7 meters per second, basically 30 miles per hour, right? It's what you drive within the city with a car. Then now, if that same alien would be looking for Earth around the sun, it would see the sun move by about 9 centimeters per second, or 0.2 miles per hour. That's really just the speed that the tortoise goes. So we're looking for these tiny, tiny velocity shifts, millions of miles away around other stars. So it's not quite straightforward, but thanks to some amazing engineers, we do have the instrumentation to do that. So then in 1995, after we had those pulsar planets, the very first exoplanet was discovered around a solar type star. which is much more exciting, of course, because if you're going to go look around solar type stars, you get into the possibility of potentially having life. Well, not quite on the planet that they found, probably, because the planet that they found had a mass similar to Jupiter, but an orbital period of only 4 days. So essentially, it is orbiting very, very close to the star. What you see here is, of course, an artist's impression. And because it is Jupiter mass, Jupiter size, and so close to the star, we've dubbed these exoplanets hot Jupiters because, well, we're not terribly original, but it sort of capture what it is. It is a Jupiter-like planet that is hot because it's close to the star. Now, it was quite a discovery, and there was a fair amount of skepticism in the beginning for the simple reason that a hot Jupiter, we don't have that in the solar system. We nowhere near anything that goes this close to the star. And furthermore, from the theories that we taught about how planets were formed didn't actually predict that hot Jupiters were a thing. So it was a very impressive work from Michel Mayor and Didier Queloz that they never gave up, that they kept an open mind. They found this in the data. They tried to explain it any other way and couldn't. And the only thing that was left is this must be an exoplanet, which was very quickly then confirmed by the American team. Now, the discovery was so, amazing and has really launched the exoplanetary field so that we could grow exponentially and are now like a solid part of astronomy that 2 years ago in 2019, they were partly awarded the Nobel Prize in Physics. So this is Michel Mayor here, and this is Didier Queloz, who works here in Cambridge, who got the Nobel Prize for this discovery. Now, these are a couple of the instruments that we do this with. They are called HARPS, and then the second one is called HARPS Nord. So on the top left here, you see the dome is the same one that you saw in the beginning. It's located in Chile, and it houses a 3.6 meter size telescope that then is attached to HARPS, which you see here bottom left. They've told me that this is what it looks like because I've never actually seen it. Because HARPS, this instrument, is locked inside a box, inside another box, inside another box, in order to keep it pressure and temperature controlled. It has to stay within like 0.1 Kelvin, 0.1 Celsius in temperature, and similarly for pressure, in order to get us stable data over time. Now, so it's I've never actually seen it. There's a picture outside of the box that I've seen. I've seen the box. They've claimed this is in it. Then the similar one, a slight upgrade, which we call HARPS Nord, was then built in La Palma on the Canary Islands, also at a 3.6 meter telescope that you can see here. And because the HARPSes are cool and are really doing what they're supposed to do, we're building another one. So HARPS 3 is currently being built in Cambridge. So that gives me every opportunity to go and see whether the thing really looks like what they claim it does. And this one will be installed also in La Palma at the Isaac Newton telescope, with first light in about 2 years. So the other method that we have, this was radial velocity. Now the other method that we have is the transit method. So this one is also relatively easy to explain. If you have a star and you look at the starlight, if there's a planet around it and it crosses between you and the star, then the light of the star will momentarily dip and then come back from the crossing of the planet. When it goes behind the star, you'll see a slight dip too, but less pronounced, of course. It's that dip from the planet transiting in front of the star that we're looking for. Just staring at a star, measuring its light, waiting for it to dip and to come back, and then modeling that to get something to infer the period, and in this case, the radius of your planet, because the bigger your planet, the more light you will block. Do you know anything about mass? not at all. So you really just learned something about the radius with this method. Just like for radial velocity, you learn something about the mass and nothing about the radius. So this one also by a PhD student, Dave Charbonnea, in 1999, so 4 years after the first exoplanet around a solar type star. He did an experiment where he just stared at a couple stars that were known to have planets from radial velocity, hoping for them to transit, essentially, and they got lucky. Now, probability speaking, statistically speaking, there's quite a high chance that these things transit anyway. So what you see here is that light and then dipping when the planet comes in front of the star, and then coming out of that again. And then here a lot of scatter because the sun was coming up. Now this planet again was a hot Jupiter. So all the very first discoveries were these hot Jupiters because they're just so easy to find. They're large, they're massive, they're close. So they give the largest signals, both in transits and radial velocity. So all the planets that we originally found were hot Jupiters. They're not at all common in the universe, we know now, but they are just really easy to find. In the meantime, this is one of the most studied exoplanets. They've looked at their atmosphere and at the evaporation and everything, basically, that they can, whenever they have a chance, they reobserve it. Now, what are the type of instruments we use for that? So the majority of transit work happens with robotic telescopes because you're really just staring at a star. So overall, this happens robotically. So on the top left, you see here part of the WASP telescopes. They are British, they're from the UK. They're not located in the UK, but they are from the UK. And these paparazzi-like cameras that you see here were originally bought off eBay, in case you're interested to build your own. And they basically just look at the entire sky, and they found almost all the hot Jupiters that there are to find around bright stars. Then top right here is MERT. It's an American robotic set of telescopes. They all look at different stars all the time. And when something happens, when something dips in real life, they're all going to point at the same time and stare at that star up until the dip comes back. So there's movies on YouTube if you want to watch that. It's actually pretty cool. And then, of course, we go to space because we can send these photometers to space. So bottom left here is Kepler, is one. It's the one that found thousands and thousands of exoplanets and really revolutionized the field. It sadly died now, so we're no longer observing with it. But there's Cheops. It's flying now, which you see here on the right, which is a very targeted mission. So really essentially looking for planets that we know already that are there, staring at them very purposefully. So it's not a detecting mission per se, but a very targeted mission, but also in space. All right, so let me give you a couple highlights. So one of the highlights that you might have heard about in 2011, that Tatooine is real, or if you don't like Star Wars, that, Gallifrey is real. If you're neither Star Wars nor a Doctor Who fan, really what it means is that there's planets that have two suns. The planets around binary stars, or even triples or quadruple binaries, is a real thing. It was a science fiction thing in most cases, and then we found proof that these things are just genuinely there as well. Kepler 16b is one beautiful example of that, where you do have two suns, which inspired NASA to make these travel posters for exoplanets. So they have a whole exoplanet travel bureau at NASA. You can order these posters. There are several of them. The one from Kepler 16b goes, "Relax in Kepler 16b, where your shadow always has company." So for a specific set of exoplanets, they've created these travel posters. You can't actually travel there, but you have the poster. Now, another highlight that I personally really like is in 2012, because there was so much data, they figured, let's just ask help from the public. Let's get the public involved. They threw all the data online. the computer algorithms had already gone over it and found everything that looked like something that we would expect. So essentially what is left for the public to find is anything special, really, things that our computer algorithms would miss. So in 2012, the first one of those, which is now dubbed PH1, stands for Planet Hunters 1, and it was a circumbinary planet in a 4-star system. So you have 4 stars, and around 2 of those, there's an orbiting planet. Now they keep doing this with the data that they have. They've recently done it with tests, but I think that data is now gone, and they currently are doing it with NGTS. Basically, it's the same concept. They have a whole lot of data, and they've shown it online, and they ask the public to look for these transit-like features and to report it to us if you find them. Now, these are all on Zooniverse if you want to get involved. Now, in the hypothetical case that you don't like exoplanets, but you want to get involved anyway with some citizen science, Zooniverse is just a treasure trove. You can classify galaxies, classify solar bursts, count penguins, whatever you want. It's filled with science projects where the scientists are asking the public to help, essentially looking through pictures or data by eye in order to find exciting stuff. Because the majority of these things, as I said, is things that our computer algorithms miss. Now, another highlight was Proxima Centauri b. Proxima Centauri is our closest star. It's essentially our neighbor. It is not a solar type star, though. But in 2016, it was found to have a Earth-like planet in the habitable zone of that star. What you can see here is the radial velocity curve of that detection. Lots of scatter, but also lots of data, and they have much more data since to show that they're right. Now, when I say habitable zone, let me just show you what I mean. The habitable zone is this concept that we use where water would be liquid on the surface if there would be water. Now, obviously, depending on the type of star, that habitable zone is closer or further out because it's really dependent on the temperature on said planet. So on the top here, you see a solar type star and you see the solar system and you see that Earth is in that habitable zone. Well, luckily. And Venus and Mars are on the edges, and then the other planets are obviously outside of it. And then when your star gets smaller all the way to like these teeny tiny red dwarfs, and then you see that that habitable zone moves in closer. So Proxima Centauri b was found in the habitable zone, but its star is so tiny that Proxima Centauri b still orbits well within the orbit of Mercury. But because the star is so small, technically it is in its habitable zone around the star. Now, there is a question, can life actually start there, because the star itself may not have enough UV power to start and generate life. Then again, everything that we know about life is based on our one data point of us. So then the final highlight I want to give was in 2017 was the TRAPPIST system, TRAPPIST-1. Now, as a Belgian, I can only be proud that it's called TRAPPIST-1. What they found here was, in one system, they found 7 Earth-sized planets that could all potentially be habitable, meaning that they are all within the limits that between where Venus, Marsish, the inner ones is perhaps a stretch, but everything else is comfortably within that same habitable zone as where the solar system planets are. Now, but here again, if you can see, this is highly enlarged. The entire system orbits well within the orbit of Mercury. The difference is that the TRAPPIST-1 star is just teeny tiny. It's a tiny star with a lot of close-in planets, but 7 in a row, all Earth size, could potentially be habitable. So that was and named after Belgian beer. So it's that was very exciting, and they're obviously still studying the system till today. Now, if we just want to go back to the same plot that I showed before, because I've talked about all these Earth-sized planets in habitable zones that are so much closer in than Mercury. So what about solar system planets? Like, are we unique or are we special? Is there loads of solar system type planets? And the answer is we don't quite know yet, because we currently can't do that yet. So I've labeled here where Jupiter would lie, where Neptune would lie, and Earth and Mars, and as you can see, they're really on the boundary of what we currently can do, because this lower right triangle of emptiness here is not because there's no planets there, it's simply because our detection technique and our instrumentation isn't sensitive enough yet to find us. We are pushing. Remember, we came from these hot Jupiters here in the top left back in the day, so we are pushing that triangle down. We've reached Jupiter, that is possible, and our next goal is of course things like the Earth around an actual solar type star. Now, if you have both the radial velocity and a transit of the same planet, now that is very powerful, because you have both the mass and the radius, and you could imagine, well, now I know it all about my planet. Not quite, because if we're speaking similar mass, similar radius, then essentially what we're saying is that Earth and Venus are the same planet, and we sort of know that that's not true. But a lot has also to do with, can we study something about the atmosphere? Can we say something about the interior structure? Can we say, because you know as well how far away you are from your star, etc., etc. So we are doing these kinds of investigations. Interior structure models are really mainly still based on having a mass, a radius, and what we know about pressure and distance to a star, etc. It is somewhat degenerate, but we can roughly say what's what, as long as your data is precise enough. And then for atmospheres, they started to study that as well. Giant planets are now routinely having their atmosphere studied. Earth-like planets, we're not quite there yet. But for essentially how it works is that the same light that comes from the star will pass through the atmosphere of the planet around it. So part of the starlight that reaches us has gone through that atmosphere of that planet and has absorbed some of these atoms and molecules in that atmosphere, so that we can actually learn what is in that atmosphere. Now, obviously, if you barely have an atmosphere, the starlight can't pass through it. And if you have lots of clouds, that may present an issue too, because the starlight may be blocked. So it's not straightforward, but there are ways that we can study these atmospheres. And one of the things that we're all waiting for, and that was supposed to be launched on Saturday and is now going to be launched in 9 days, I hope, as a lovely Christmas present, they're going to shoot up JWST, James Webb Space Telescope, which will look at lots and lots of atmospheres of exoplanets. Now, in the end, the ultimate goal is that we want to find an Earth twin, and here in Cambridge, we are trying to do that. As I said, HARPS-3 is being built here, and it has as its primary goal to show the capability of finding an Earth twin, so really an Earth-like planet around a solar type star in an Earth-like orbit. Thank you.
Wonderful, Annelies. Thank you so much. It's such a fascinating subject. It's always so exciting hearing about something which is like on the edge of what we can do with our technology, but also just conceptually on the edge of what we can do with human knowledge, right? We're finding these answers to questions like you were saying, go back to Epicurus and beyond. It's incredibly fascinating. So anyone that has questions for our speaker, you can pop them down there in the YouTube chat. Before we do, I wonder if you speak a bit more about JWST and what JWST is going to bring to the field of exoplanets. I know it's going to be very good at finding, is it molecules of biosignatures in atmospheres? I don't know, if you could speak a bit about that, that'd be fantastic.
So James Webb is going to look at a whole bunch of atmospheres of Neptune-size and Jupiter-size planets. Earth-sized planets will be beyond reach for JWST, but it will be able to do all these these in-between planets that we found in the meantime. So we found all these types of exoplanets that are in between an Earth and a Neptune. In the solar system, we don't have anything between Earth and Neptune in size or in mass. Turns out that the universe is filled with planets between Earth and Neptune. So we have all of them with very little basis of what they are, because we don't actually have a similar one in the solar system. And JWST will be able to look at the atmospheres of these planets. Because it is in space, it makes it already a whole lot easier, because doing this type of work from the ground obviously means that that starlight that has passed through the stellar atmosphere and then through the planet atmosphere then passes through our atmosphere, making the data horribly complicated, of course, if it passes through two planets' atmospheres. So going to space takes away one of these atmospheres, our own, making it a whole lot better to actually look at the atmospheres of these smaller planets. The Earth-sized planets will be beyond reach.
Wonderful, thank you. Lots of people in the talk saying thank you sorry, lots of people in the chat saying thank you for a lovely talk. It's a question that's coming from Nikki, who wants to know, is it true that the sun is an unusually quiet star and that other stars are often a bit more active? And does that have any implications for life on Earth? Or for the evolution of life on Earth, I should say?
Well, Nikki, there was debate about that. I've heard people call the sun unusually quiet. I've heard people say the sun is normal, and I've heard people say that the sun is more active than its brothers, so to speak. I'm personally of the view that we're average as compared to other solar type stars, like stars with the same mass and radius as the sun. There's no indications that we are in any way on a boundary. So there seems to be that we're quite normal. Obviously, at the moment, we're probably quieter because, as you may know, the sun goes through a cycle. It goes through a magnetic cycle every 11 years or something. We're currently just coming out of a minimum. So if you would look at the sun right now, yeah, it does look a tad boring. If you would look in like 4 or 5 years, then you would see that there's a whole lot more going on the surface of the sun. Now, there's been studies led from here, actually, I think in Cambridge by Paul Rimmer, who've studied which type of star would be ideal for creating life as we know it, of course, with the mixture of having enough UV to start life, but also not be too close so that you have these disrupting stellar winds that may take everything away again. And things like G-type stars, like sun-like stars, seem to be that sweet spot of creating life in their habitable zones.
Wonderful, thank you. Another question has come through. Are there plans for another Kepler-like mission? Because Kepler obviously only lasted 4 years, and TESS, while it's going to be fantastic, is going to be working in quite a different regime. Are there plans for a sort of a Kepler clone to do what Kepler is doing, but maybe for better and longer?
That is a very good question. There's similar sort of missions, not quite exactly the same. So one downside of Kepler was amazing. Obviously, it found thousands of planets, and for statistical purposes, what the types of things that are out there, it was brilliant. The problem with Kepler was that they really looked at a very small field in the sky, but they looked very deep and for very long. But a lot of the planets that they found are around stars that are somewhat too faint for us to study them in more detail. So that was somewhat of a downside. So the next mission that flew, which is currently flying, is TESS. And TESS took the totally opposite approach, and they were like, we're going to look to the entire sky, and we're going to focus on the bright stars only, so that people on the ground with other instrumentation can then follow up whatever we find. And they've been finding a whole lot of stuff that, a lot of telescopes are then chasing after to know more about them. And then the next one in line for some sort of similar mission will probably be Plato. Plato is a European mission that They say will launch in 2026. I'm a tad skeptical that that will actually happen, but the end 20s, this will launch, and they will likely stare for 2 years at a field in the north and stare for 2 years at a field in the south, a field which is about 4 or 5 times larger than the original Kepler field. There's currently talk that we're likely going to choose a big field that encompasses Kepler so that we can study Kepler again, but then much more around it. And of course, also stare at it for a very long time, hoping to catch that Earth-like planet in transit.
Wonderful. Well, it looks like that is all the questions. Well, thank you so much, Annelies, for such a fantastic talk. It's such a fascinating field of science. I can't wait to see what happens in the next few years. And thank you to everyone watching at home. I hope you have had I hope you've enjoyed this series of Wednesday Talks. We are back on the 5th of January, and it is going to stay online only for the foreseeable future with obviously the Omicron situation. But we're going to continue having fantastic talks every single week and stargazing when we can. So enjoy your Christmas break, and we will see you in January.
Thank you all.